If you're not familiar with stress balls, a stress ball is a foam ball that people squeeze, and it's supposed to relieve stress. But you squeeze it, and then so you put it in your hand, you make a fist, and you squeeze it, and then you open your fist, and the ball bounces back out to its original size. This requires energy, right? It takes energy to squeeze a stress ball. You're doing work on that ball when you squeeze it, but some of that energy is lost as heat as it's squeezed. Now, this is not always noticeable. It doesn't feel hot. It's not going to burn your hand, but some of that energy is lost when that ball gets deformed. The relative motion of the particles that make up the ball generate heat when they move relative to each other. So if you have a system that contains a stress ball, the system has 22 joules of internal energy. Okay, so everything has internal energy. The particles are always moving. All molecules are always moving. So this particular stress ball has 22 joules of internal energy. When you squeeze the ball, you're doing 5 joules of work. It takes 5 joules of work to squeeze the ball. Well, at the same time, the deformation of the ball is going to result in some generation of heat. In this case, 3.5 joules are going to be lost as heat. So, what's the new internal energy of the system? We can draw a diagram like this that shows the system. The system initially has 22 joules of internal energy. It has five joules of work done on it, and 3.5 joules of heat are lost. So we would take the initial 22 joules, we would add that 5 joules of work, so we'd get 27 joules, and then subtract 3.5 joules for the heat that is lost. So 27 minus 3.5 is 23.5. And so then what that tells us is that after squeezing the ball, the ball now would have 23.5 joules of internal energy because you've done work on it. You've added that internal energy to it.